Hi everyone, I'm Jamshed Damkewala. I'm a TPM at Microsoft, and one of my areas of focus is giving developers the tools they need to take their cloud-native apps to ARM. In this video, we will do two things. First, I will share a bit about Azure Cobalt 200, Azure's own silicon, purpose-built for the cloud, and how this is reshaping the price-performance conversation for our customers. The customer excitement behind Cobalt has been remarkable, and what is coming next with Cobalt 200 is the most exciting roadmap I have worked on in years. Second, I will show you a demo of how we take a real cloud-native app built with microservices and migrate this from x64 to ARM and deploy to AKS running on Cobalt 200. So, let's get started. We began this journey with Cobalt 100, our first Microsoft-designed cloud CPU. Its impact and the feedback from external customers and our own Microsoft teams shaped Cobalt 200. Cobalt 200 takes the next step, a new architecture, a refined design, and a real step change in performance, delivered through entirely new VM families engineered for a wide range of workloads. It's built for the workloads defining this era of cloud computing. Cloud-native services, agentic AI, where developers spend most of their time today, containerized microservices, distributed data pipelines, vector search, retrieval, model orchestration, and agent runtimes. These workloads are concurrent, memory-aware, and I/O-sensitive, and they need to be cheap to run at scale. That's why Cobalt 200 ships not as a single SKU, but as a full portfolio expanding on Cobalt 100 with high memory optimized and dense local storage optimized VMs. And it's our most power-efficient Azure compute offering yet. Cobalt 200 is a major leap forward at the silicon and platform level. More compute cores, more cache, and faster memory, built on the latest ARM architecture with TSMC's 3nm process. It's delivered on our newest cloud infrastructure, with Azure Boost providing accelerated I/O and networking built in out of the box. The result is up to 50% higher performance than Cobalt 100, Azure's leading performance offering in the market. Let me talk about scenarios where Cobalt really shines. First, digital and cloud native. This is the heart of where customers deploy Cobalt today. Scale-out and web-tier services, microservices, and containers, the engine room of modern cloud applications. It's also where developers building for Windows 11 on ARM use Cobalt as a native cloud target that mirrors the client experience their users run on, keeping the dev-to-deploy loop tight. Increasingly, agentic AI lives here too, and Cobalt 200 delivers the per-core performance, density, and cost efficiency these workloads demand. Cobalt also shines in modernizing the enterprise estate, where customers can move established workloads onto Cobalt and unlock a step change in performance and efficiency. Workloads built on .NET, Java, Python, or Go port cleanly, and open-source databases, in-memory caches, data processing, and analytics engines all run beautifully. For most teams, it's recompile and go. The heavy lift you may be imagining is rarely there. To make this even easier, we've partnered deeply with ARM on migration tooling. Through Azure's own porting frameworks and the ARM partnership, migration guides, dependency analyzers, and runtime support across all major languages are available today. What you're looking at is Cobalt 200 per core performance, measured relative to Cobalt 100 across three lenses. On the left, industry-standard benchmarks, the vendor-neutral, repeatable measurements your engineering teams trust. Across the board, Cobalt 200 delivers a meaningful generational leap. In the middle, our own Microsoft benchmarks, broader, more diverse, workload coverage that mirrors what actually runs in production. It's the same story, a clear, consistent step up. On the right, the strongest signal of all, Microsoft's own first-party services running at hyperscale on real customer traffic every day. Workloads differ, and yours will land somewhere along this distribution. But every bar tells the same story. Cobalt 200 raises the floor on per-core performance. For developers, that means more work done per core, fewer cores to provision, lower bills, and real headroom to scale. Accelerating agentic compute is where Cobalt 200 matters most. First, The industry is converging on a new way of thinking about performance for agentic workloads. It's no longer just about throughput on a single request. It's about how fast you can spin up an agent sandbox, how quickly that agent becomes responsive, and how many you can run concurrently on a single machine. Second, the time from requesting an agent sandbox to doing useful work is meaningfully faster on Cobalt 200, consistent with the per core performance story I showed earlier. Third, because Cobalt 200 delivers more useful work per core, you can pack more agent sandboxes onto the same VM and more agents onto the same fleet. That translates directly into lower cost per agent and higher concurrency for your users. Now that we've seen the power of Cobalt 200, let's see it in action. Here's a quick overview of the demo you're about to see. We'll take a real cloud-native application with 10 microservices deployed to AKS. We'll start by building and deploying it locally, and then explore the power of multi-architecture images and deploy our app to AKS on Cobalt 200. Finally, we'll see the performance of Cobalt 200 by running a local inference workload on CPU. No GPU, no OpenAI endpoint in the cloud, no paying for expensive tokens. Let me first introduce the application I'm going to use. This is .NET eShop. It's the official .NET reference application for cloud-native development. An online storefront with a product catalog, a shopping cart, checkout, and user sign-in. It's open source, and you can find it on GitHub under .NET/eShop. Under the hood, it's a proper microservices architecture, the kind you'd actually run in production. There's a Blazor storefront, the web app, that customers see. Behind it sit a set of independent services, identity for sign-in, a catalog service for products, a basket service for the cart, and an ordering pipeline. There's also a webhook service for outbound notifications. And those services lean on 3 standard open source backends: Redis for the basket, Postgres for orders and product data, and RabbitMQ as the message broker. So in total, we've got around 10 application services plus those 3 backends. We're going to deploy and run this app twice. First, locally, on this x64 dev box using Docker desktops built in Kubernetes, and then on a Cobalt 200 AKS cluster. Same source code, same container images, same Kubernetes manifests. The thing I want you to watch out for is how little has to change to move a full cloud workload from x64 over to Cobalt 200. All right, let's start building. First, I need to store the container images I'm about to build. That's what an Azure Container Registry is for, and it's a single place both my local Kubernetes cluster and later my Cobalt 200 cluster will pull those images from. I'm already signed into Azure, so I'll create a resource group and the registry. Before I can push to the registry, I'll do a quick check that the Docker engine is up. That's because the registry login writes a token into the Docker credential store, and it fails if the daemon isn't reachable. Good, the engine's running. Now I log into the registry. Before I start building, let me set up what this application actually needs, because it explains why I'm about to do what I do. The images fall into 2 groups. First, the application services themselves, the storefront web app, plus a set of backend microservices for identity, the product catalog, the basket, ordering, payments, and webhooks. These are the .NET services I'm going to build from source and push into my registry. Second, a few standard open source backends the app depends on: Redis, RabbitMQ, and Postgres. Those I'm not going to build. They're stock images, so I'll just let Kubernetes pull them straight from Docker Hub when it deploys. Now I'll build the application images. I'll go through each service, building it from its Docker file and pushing it straight to my registry as it builds. That's the storefront and all the backend services built and pushed. Let me confirm everything landed. There they are, all my application services sitting in my registry. Quick word on how I'm going to deploy this. I'm using Customize, which is built right into kubectl. The idea is simple. There's a base which holds the shared Kubernetes manifest for the whole app, the deployments, the services, all of it. And then there are overlays that sit on top of the base and patch only the handful of things that differ between environments. It's just small patches layered onto the base. So I have 2 overlays, one for my local Docker desktop cluster and one for the AKS cluster on Cobalt 200. The differences between these are tiny, things like which ports to expose, the public host names, and the identity URL. The application, the pods, the wiring between the services, all of that lives in the base and is identical no matter where I deploy. Let me make this concrete with one example. Here's the web app service in the base. It has a cluster IP on port 80, which means it's only reachable from inside the cluster. That's the default and it's same in every environment. Now here's a local overlay, and this little patch targets that exact same web app service. It changes just two things. It flips the type to load balancer and it sets the port to 8080. So what we've done is layered a tiny deployment environment specific tweak on top of what was already defined in the base. There's one thing each overlay does need from me. The base refers to images just by a short name, like eshop/webapp, with no registry attached. So I have to tell Kubernetes where my images actually live. Customize, edit, set image rewrites those references in the local overlay, and I'm running it inside a simple for loop so I don't have to type the same command out once per service. My application services point at my registry, and the 3 open source backends point straight at Docker Hub, so Kubernetes pulls those overlays publicly when it deploys. First, I'll point kubectl at the local Docker desktop cluster, create a namespace for the app to live in. Docker Desktop's Kubernetes doesn't automatically reuse my Azure login, so an image pull secret is how the local cluster authenticates to my private registry to pull the application images. The Docker Hub images don't need it, they're public. Now we deploy. Kubectl apply with the -k flag tells Kubernetes to run customize, merge the base with the overlay, and apply the whole thing. As the pods come up, the cluster pulls my application images from my registry, the open source backends from Docker Hub. You'll probably see a Windows Firewall prompt pop up right about here. That's because Docker Desktop's Kubernetes is opening up the load balancer services so I can reach them on local hosts, and Windows wants permissions to allow the network access. So I'm going to click Allow. With that applied, I'll wait for every deployment in pod to report ready. And there's the whole stack running on my local machine. I'm going to take it for a spin. I'll open the storefront on localhost. I'm going to log in as Alice. And I'm going to browse the catalog and let me add something into the basket. Everything's working. This is all running on x64 on my dev box. Now the interesting part. We're going to take this exact same app and deploy this to Azure Cobalt 200 with very minimal changes. The Cobalt 200 cluster I'm about to create runs ARM64. If you think back when I built the images, they were x64. This is where multi-architecture container images come in. Instead of maintaining separate images per architecture, I can build a single image manifest that holds both an x64 variant and the ARM64 variant under the same name and tag. Kubernetes will then pull whichever one matches the node it's scheduling onto. So I'm going to rebuild my images as multi-architecture, and you'll see the change is trivial. Let's rebuild. Look closely at the platform flag and compare it to earlier. The only difference is I've added a comma Linux/ARM64. These are same Docker files, same source code, same tags. I'm just asking BuildX to produce both architectures this time. The eshop Docker files is set up so we cross-compile natively for ARM, so there's no emulation involved. The build can take a while, so I'll speed up through it. Let's inspect the storefront images manifest to confirm everything looks good. There it is, Linux/AMD64, Linux/ARM64, both living under one tag. Now let's stand up the cluster. I'm going to create an AKS cluster with 2 nodes. The key part is the node VM size, standard D8 PDS v7, which is a Cobalt 200 ARM64 size. I'm also attaching my registry to this cluster so AKS can pull from it. Provisioning the AKS cluster takes a few minutes. Cluster's up. I'll pull down its credentials and switch over to the new AKS context. Now let me confirm what I'm actually running on. 2 nodes, status ready, architecture is ARM64, VM size is D8 PDS v7 as we expect. These are Cobalt 200 nodes. I need to do the same registry update I did earlier when running local, but this time on the AKS overlay. The AKS overlay only changes environment-specific things, the load balancer, the public DNS names, and the identity URLs. First, I point all my application images at my registry with the same for loop I used before. And the open source backends, Redis, RabbitMQ, Postgres, point straight at Docker Hub. Now, I deploy to AKS. We again run kubectl apply -k, just pointed AKS overlay this time. That one command deploys the entire stack, all the application services plus the backends in a single shot. AKS will pull each image from my registry, and because they're multi-architecture, it grabs the ARM64 variant for these Cobalt nodes. Now I just wait for every deployment in pod to report ready. Everything's up. Let me confirm the pods are running. Yep, all running. And just to make sure, let me ask the web app container what architecture it's actually on. We see AR64. That's my storefront, the exact same source I ran on x64 a few minutes ago, now executing on Cobalt 200 ARM64. Let me open the storefront on its public Cobalt 200 endpoint and run through the same flow again. I'm going to log in. I'll browse the catalog and let me add an item to the cart. Everything works. I did not make any changes to the sources for the app. I did not change my Kubernetes manifest beyond the environment overlay. The one thing I changed was adding ARM64 to the platform flag when I rebuilt the images, so I built multi-architecture images. Kubernetes pulled the right architecture on its own. That is the value of the multi-architecture container strategy. There's one more thing to show. The storefront has a chatbot that's been hidden this whole time. I'm going to power it with 5.4 Mini, a 3.8 billion parameter model running on CPU inside the cluster on Cobalt 200. Let me talk about why running it this way matters. The model runs right here in my own cluster on the Cobalt CPUs I already have with no GPU needed. There's no OpenAI key, no per token billing, and inference just uses compute I'm already paying for. And nothing leaves the cluster. The customer's questions, the prompts, the product data, none of it gets uploaded to a third-party API or a SaaS endpoint, and there's no internet round trip at inference time at all. For workloads where data privacy, predictable cost, or running disconnected matter, that combination is a big deal. The first thing to do is build the images for this service. The inference service hosts the model and runs it on the CPU using Onyx runtime. To keep it self-contained, the model files get baked right into the image, which is why this one is large and why I built it in 2 stages. A small image that just holds the model files, and then the inference image itself, which copies the model out of that one. So the order matters. First, I'm going to download the model files with this prepare model script. Then I build both images, multi-architecture, so they run on the Cobalt nodes. This is the biggest build today because the model lives inside the image. I'm going to speed through it. Now we wire it up. The inference deployment has actually been part of the cluster all along, just sitting at 0 replicas because we weren't using it. So first I'm going to scale it up to 1, and that pulls in the image I just built. Then, 2 environment variables wire the app to the inference service. The first turns the feature on, the other tells the app where to reach the inference service inside the cluster. I'm going to set those on the storefront and the catalog service, and Kubernetes does a rolling restart. When this will come back, the storefront will register a chat client, and the catalog service will register an embeddings generator for the semantic product search. If I look at the storefront now, there's a new chat icon in the bottom corner that wasn't there before. It's going to start off as gray while the model warms up, and once that's loaded, it's going to turn blue. It's blue now, so I'm going to click on it and ask it to show me watches. And there are product cards with images, names, and prices. That came back in well under a second. A 3.8 billion parameter model running on CPU inside a Kubernetes pod on Cobalt 200. A few things stack up to make that quick. ARM ships an open source library called Clyde AI with kernels tuned for these Neoverse cores, and Onyx runtime automatically uses them for the math. The container warms the model at startup, so it's ready before the first request. And the runtime is tuned to use the cores available in the pod. Let me show you the multi-turn behavior because that's where it gets faster. I'll follow up in the same chat with add the first one to my cart. Notice it understood the first one because it kept the previous turn's results in context and picked up the right tool, add to cart. So that's the whole journey. We built a real .NET Microservices app as container images on a Windows x64 dev box, validated it on a local Kubernetes cluster and Docker desktop, and then deployed it to AKS on Azure Cobalt 200. All of them from one set of image tags. The only change to get to ARM64 was adding ARM64 to the build platform flag. Then we served a real 3.8 billion parameter language model running entirely on Cobalt 200 CPUs to power the storefront's chatbot. I did not need to rewrite anything, make any changes to the sources for the app. Multi-architecture images let Kubernetes pick the right architecture for the node, and local AI inference allowed us to deliver intelligence without using an API key, GPUs, or paying for expensive tokens, since we ran this on the same CPU we are using for the rest of the app. Before we wrap, here are some resources to start building on Cobalt today. On the Azure blog, you'll find real-world Cobalt 100 customer stories, and the Cobalt 200 announcement blog offers a deeper technical narrative. The ARM migration overview includes ARM learning paths, and the ARM software ecosystem dashboard lets you confirm the libraries and runtimes your stack relies on are ready. Finally, the Azure Cobalt VM documentation on Microsoft Learn has hands-on guidance. I'm incredibly excited to see what you build next on Cobalt 200. Thank you.